Where is the cord so I can show it to the people in the room? There we go. All right. So tonight we're going to do 3 different topics. First one is going to be dimension reduction with principal components. So here the goal is to just run through an example of what we can do, how we can approach this, and how we can actually use this. Minimize that. All right. So principal components, it has several uses. One is for study of correlation between our variables. One is for looking for under the hood hidden latent variables. That's called factor analysis. It's principal component analysis is the simplest version of factor analysis. The one that we're going to talk about tonight from a machine learning point of view, the one that's most important to us is dimension reduction. So imagine the idea that I just have too many predictor variables to wade through. Like there's just too much going on. I have, let's say, conceptually, pretend that I have thousands and thousands of columns of data that I could use to predict a target variable. Now, something to consider about that is that if I have that many predictors, I have to somehow limit that down. Because first and foremost, if I have a lot of predictor variables, the more predictor variables I have, the more likely to overfit I am. That's true for any machine learning model. If I just keep on throwing in more and more predictor variables, I'm more and more likely to overfit. We only want to put in good variables in our model, even if the model will do variable selection for us. Because there might be, like from our point of view, random fluctuations in the data that will make a predictor variable look like advantageous and favorable when it's not. So we want to use subject matter knowledge and machine learning techniques to choose only good variables. All right, if I have a lot of predictor variables, I've got a needle in a haystack situation. It's just a lot of stuff to go through, a lot of stuff to work through. It's just overwhelming. I'm going to need to mute people. How do I mute people? Yeah, I need to put, hey, let's do this. Mute, there we go. All right, so now, so yeah, if I have a lot of variables, it also gets more difficult to interpret. So let's say I'm doing a tree model and I have 2 variables that are highly correlated. They're not exactly perfectly correlated, but they're highly correlated. One thing that you'll notice is that if I was to just take one of them, there's a certain number of times that would be predicted by like my random forest. If I have both of them and they're highly correlated, it's kind of like it gets split out. The number of times that the variable gets selected, if I rerun it, will be about 50-50 between them. So then what could have been a very informative variable by itself, it gets muted because of the correlation between. So we don't want to be dumping in stuff, when I go back in to interpret things. Now, remember, if your client wants you to keep like two correlated variables in there, you still do it anyway. That's something I've bumped into professionally, is that the client wants particular variables in certain structure, something like that, because they believe that it's useful. You work with your client, do what it takes to get them to buy in on the model. If they don't buy in, your model is useless. So that's always our #1 priority. Now, so how do we tackle this situation? Well, one thing that we can do, we can run manual variable selection, and that's, there's something you can look at correlation, you can automate it, run code to do things to give us some guidance. But if I have a lot of variables, that's not really going to be all that feasible. Then we could select a model that performs variable selection automatically, which frequently will save us from problems, but it's better to not have excess crap in there. Another option that we've talked about is variable clustering. So remember, in variable clustering, I take all my variables, all the ones that are correlated with each other, we put them into a group, and then either we select a representative from each group, or we do principal component analysis on the group and use the PCA as a predictor. And then last but not least, dimension reduction. All right, so potentially all formats of matrix factorization could give us a technique to do dimension reduction. The two big ones are going to be principal component analysis and then non-negative matrix factorization. Those two are the big ones. Now, in this course, I've also talked about stochastic neighbor embedding with T distribution. This looks very favorable in the toy examples I've played with, but it takes a long time to run. And since it takes a long time to run, I've never actually used it because it just wasn't worth it. Because anytime you're running a project, you're going to end up rerunning your code over and over and over. The performance benefit I've seen really wasn't worth that time aspect. So PCA is by far the heavy hitter on this. It's the most common. Non-negative matrix factorization comes up most frequently with text analytics, specifically bag of words. So if I'm in a situation where I'm going to have binary vectors, binary columns, or count columns, that's usually when we invoke this. All right, so let's go ahead and run through an actual example. So the first thing I'm going to do, of course, is load my data. And this is the meter data set that I've got floating around in the course. And what we want to do, we want to be able to predict the health of a meter using other columns of data as our predictors. And so if I look at the dimensions, I've got 92 rows, 52 columns. Now you'll notice that that's kind of a bad ratio. Right off the bat, I don't want to have proportionately fewer than 2 rows of data per predictor variable. You always want to consider that ratio. That when I have parameters, think of it from a regression point of view. How many of us have taken multiple regression and had to think about like the number of parameters? Anybody? No, nobody. The entire class.
We were kind of advised that sometimes use multiple regression, but I think what was it, like machine learning, they pretty much said, oh, you're probably going to go off and do something else and you start getting multiple regression.
Yeah, so multiple regression does one of the things that gets missed in going from multiple regression to machine learning is that when I have a lot of parameters, if like the ratio of rows of data to my number of parameters is low, what's going to end up happening is I'm going to be more prone to overfit. Imagine if I was to do a neural network and I was to go with, let's say, 90 parameters in that neural network. Well, what's going to happen is it's going to look like an absolutely fabulous model. And the computing of, the number of parameters for a neural network, that can get a little bit complicated. Like, are we doing a skip layer? Or, do we have the bias term? How many weights are we using? And depending on, number of hidden layers, number of, nodes we have, it can be a bit of work. But like, just think about the ratio of the number of parameters you have in your model and your rows of data. So you always want to have, my personal way that I go, I like to have, at least 30 observations per parameter in a model, right? Now, does that sound like consistent with the rest of statistics? When is it that we feel like we have the normal distribution? when we're doing T?
30.
30, right? So basically, just off of that, I just say I want 30 rows of data per parameter. That's just my eyeball way. That way, as I'm looking through it, I feel like I'm not going to put myself at risk of over parameterizing my model. I've not seen that written down anywhere. I just feel like that's a good benchmark for what I'm doing. All right, so here I'm looking at that and I'm like, wow, that's not a lot of rows of data. So I know off of this point of view of trying to have not too much going on, I want to definitely reduce down the number of predictor variables I have. And now 52, honestly, I could automate that, work through, do variable clustering, something like that. But let's pretend conceptually that I've got thousands of columns to work through. How am I going to tackle this? All right, so our target variable is a categorical that we've got gas injection, healthy, and waxing, and we want to be able to predict. Okay, so as I work through, I'm going to be generating some visualizations, and what I want to have a color for each of these levels as I work through. That way, so remember, when you have a visualization, you always want three things. You want geometry, you want color, and you want labels. Always want those three things every single time. I have just about made my career based off of that one slogan. Get those three things going. So I'm going to use the Matrices color palette. This is a very good color palette for those who are colorblind. What it does, it takes darkness, color of the rainbow, and hue and intensity, and it's selected the colors so that they all are on a gradient. And so if someone is colorblind, they can still figure out what's going on. And people tend to not make mistakes with this. And so here I'm just going to take the color palette. I'm making a vector, and I'll use it later on down the road for coloring. All right, so conceptually pretend that we just have too many variables to work through. One option I have is I can do dimension reduction. And in the dimension reduction, what I'm going to do is I'm going to take my 1,000 column data, and I'm going to find the best approximation in a smaller subspace. So if I was to do just one principal component, that'll be the best one-dimensional representation of my data I could possibly get. If I was to go with two, that's going to be the best two-dimensional approximation of my data that I could possibly get. And then three dimensions, and so on. Now, when I say this, what is when I say best, what's the criteria for that? This is going to be in terms of Euclidean distance. So the distance, take the coordinates, subtract them, square them, all of them, add them all up as the difference. And so now as I go through this, what we're going to do effectively is the result is the first principal component by itself is the best one-dimension representation. Now, when I go to the second principal component, that's the best one-dimension approximation after I've considered the first one that's already in there. So 1 and 2 together give me my best two-dimensional representation. And then 1, 2, and 3 all together give me my best three-dimensional approximation, and so on. And so you can think of this as if I was to have 4 principal components, that is the best 4-dimensional approximation of my data I could possibly get. You had a question?
Yeah, when you do that, like your first, second, third best principal components, that kind of count. If you're going to be doing regression on that counts as multiple regression.
Yeah. So yeah, when you would drop these in, these would end up being multiple regression. The people on Zoom can't see this, but if this was my data, I'm exaggerating. Let's say that this is variable 1 and this is variable 2. I'm exaggerating this as being a line, kind of just to emphasize what the first principal component looks like. Is that here, if this was my data set, my two, let's say I only had 2 predictors, what would happen is that if this is 0 on there, then this position here is this point's PCA 1. This location here is that point's PC1 also. Here is this point's PC1. This one's PC1. And you can see that it goes to the closest point on the line. Now so if this is principal component 1, principal component 2 goes perpendicular like this. And it starts picking up the position on this perpendicular line, perpendicular ray. And then if it was higher dimensions 3, we'd be going out this way.
Use one of the ways.
Oh, okay. All right, how do I change that? Thank you for letting me know. Okay, hopefully that's good. Okay. All right, so we're going to go through and we're going to do our principal component analysis of this. All right, so what I want to do after I get my data is I don't want my target variable in here, because what I'm going to do, I'm going to use these reduced dimension columns as my predictor variables. And so if I'm doing something on my predictor variables, I don't want my target variable in there. So I'm grabbing everything but my target variable. Now, when I do my actual principal component computations, I'm going to put in my data. Now, something that is important to be mindful of, you don't have to center, you don't have to scale. By default, R automatically centers and scales your data. In general, you want to do that. If you don't center and scale your data, so centering is subtracting the mean, and then scale is dividing by the standard deviation. So the scale step is the one that's usually more important to run through. What will tend to happen is that if I don't do this, columns that have greater variance, sample variance, greater standard deviation will end up having more influence on my model. And so if that's how you want it, that's good. Let's say I'm in a situation that all of the columns of data are on the same scale and they're all like relatively close to each other. If I've got one that's like crazy big variance and then all the others are all pretty tight, in that situation, I would want to rescale. But if it's close, relatively speaking, everything looks like it's on the same scale, nothing's too far out, I would not bother to center and scale my data. All right, so now after I get my principal components computed, I want to take a look at what I've got for my outputs. All right, so here I'm going to take the summary, and I'm interested in the importance, and here I'm rounding just to make it a little bit easier for us to look at. So the number of columns I drop into PCA is the number of principal components I will get. Potentially, if I had 1,000 columns of data, I could go and get 1,000 principal components. So for every dimension of raw data I have, that's potentially how many dimensions I could have of orthogonal directions. We don't want all of these. Well, almost surely, we're not going to want all of them. Here, this is telling us, this gives us a sense, the standard deviation gives us a sense of how far out it is from like this center point to here. So this is, I mean, it's not exactly a one-to-one correspondence because it depends on data spread and how many, where the points actually are. But you can think of it approximately that the standard deviation is measuring how far this part of the cloud is. And so here, if I make this part, we can see that this is a much smaller standard deviation on that second principal component. That in this scenario that I've drawn on the board, the first one is accounting for almost everything. And the second one picks up really what's left. It will, because of the scheme of going like the best one dimension direction, then the best like second, best third, and so on, this will always be a decreasing sequence of numbers. So what we want to do is we want to look at this and we want to figure out how many do I need for my model. And so I don't want too many, but I don't want too few, right? Something to always be mindful of when we're fitting our model. It's better to underfit than overfit. It's just take that point of view. Now, if I can get spot on, of course I want spot on. But if I'm like, oh, is it a 4? Is it a 5? I would go with a 4. All right. Now here, this tells us the proportion of variance accounted for. And here's the cumulative proportion of variance accounted for. And you'll notice that it's going up until here. I mean, it's just meaningless. These are just such small numbers. I know just looking at this, I'm definitely not going to go up to 12. All right, so now looking at that, I need to make a choice. How many am I going to use? Well, it's kind of hard to read, right? I mean, I know that 12 is too many. Let's get something to help us out. All right, so now a biplot is a very common way of plotting things, and this is not applied. So the biplot is used to give us an idea of how much does each variable contribute to each of the principal components. And so it really didn't plot well on this one because this is so large. But what we would see if I use one of the other plots that we had in the other lecture is we would use the arrows. They're all tied up in here. Hard to see because they're on top of each other. But the length of the arrow going horizontally tells us how much is that one variable contributing to principal component 1. And so if it has a large arrow going to the right, it has a large influence on that, and it's a positive number. Well, over here, if it was negative and a large, it would tell us it has a large amount of input, and it would be a negative going in the opposite direction. And then the second principal component, where the arrow is by position vertically, tells us how much it's influencing the second principal component. And so this is the primary use of this, and for this demonstration, it really didn't work out too well. This will help us like see if I want to interpret what are the principal components. For us, for machine learning, usually it's not a big deal. If I was to do like psychometrics, it's a much more important aspect. All right, so now principal component Scree plot. All right, so this is telling me the proportion, or this is the amount of variance accounted for by PCA1, amount of variance accounted for by PCA2, 3, 4, and so on. Now, as I look down this, you can see that's decreasing. And so if I was to keep on adding ons, if I'm here and I chose, or well, actually, let's say that we were to go 1, 2, 3, 4, 5, 6, 7 principal components, and then go instead of 7, I go 8. I've definitely hit diminishing returns. I'm not really gaining anything. So where we want to do, or where we want to grab, we want to find what's like an elbow. All right, so remember when you were in calculus, you had to find like concave up, concave down. We want to find the point of diminishing returns. And so visually, It's kind of like, trying to find where the second derivative switches, but it's a discrete points plot. It's not actually a smooth curve. Looking at this, where do we feel like we hit diminishing returns as we go from left to right? That all of a sudden we see like a big drop. 2 or 3, yeah. So we can kind of see here, and then the rest is kind of flattened off. Maybe by someone else's eyes, they can look and see that, well, all right, 3 is okay, but the rest of this, we see that we've got diminishing returns if I was to keep on going over. And this is ultimately a subjective call on what to go with. But this is, in my opinion, the most important one. And like if you're working on a project and your coworker or your boss says, "Oh, it must be this one off of Scree Plot," just go with it. It's ultimately just where it is a subjective call. All right, so I'm going to go just kind of a little bit high on this one, just to make sure we kind of see what's going on. So I'm going to go ahead and go with 6. So 1, 2, 3, 4, 5, 6, and from here on out, it's definitely, I'm just going to drop everything after that. Now, if I was to know beforehand, like what was the maximum number I would use, or if I was to just know I'm going to use this many, I can actually tell the PR comp function to stop at that many. So up here, when I did the calculation, let's say I knew I definitely was not going to use more than 6. I could tell the function up here to go with only 6, and it would stop at 6 for me. And that way I don't have the extra computation time. All right, so here I'm going to go ahead and grab my principal components. So something about the output in PR comp is that it calls it just X. I personally hate X as a name for anything in coding because it is the least descriptive name possible. But so here X is going to be the actual principal components, and I'm specifying that I want columns 1 through 6 on this. So PCA 1, PCA 2, PCA 3 up to 6. So now let's do a pairs plot just to see what's going on. What do we see when we look at these scatter plots from a machine learning point of view? So my goal is to predict the color using the principal components. So what I would really like to see, I would like to see that ideally, I would like to see a corner by itself have one color. Ideally, I would like to see another region of color points by itself, and another region of color points by themselves. So I would like to see very clear distinctions of the region of the colors. So I would like to see like separation between those colors. So if I look at, let's say 5 and 6, does it look like I have good separation? What about 3 and 6? Or 3 and 5? Does it look like the color points are separating themselves out? Or does it look like I have colors like next to each other?
Seems to me like a lot of them are in each other.
Yeah. So that's what we don't want to see. What I want to see is something a little bit more like this. Now I've got overlap between like the green, but I can kind of see that there's a separation at least between yellow and purple. That, and now of course there might be points like overlapping with each other on the scale. It might be, it's zoomed in, digging into the data, I might find something a little bit easier to see it. But here, it looks like I've got a separation between yellow and purple. And so that would be very helpful for identifying the state, right? So let's see what happens. All right, so looking at that, if I zoom in, I mean, I can see like all of the teal ones are here. I've got all the purples have a separation from the yellows as nice as I could possibly hope in this problem. So I can see that like separating yellow from everything else is just along PC2, right? And then here, PC1 separates the teal from the others. So I'm feeling like I might be able to get away with just 2 principal components. That's a huge reduction, right? All right, so I could just go with those 2 in there. Now, what does each principal component tell me? So remember, I've taken my data, and from a math point of view, I didn't worry about what the measurement was. I just dropped the numbers into an algorithm. And that algorithm doesn't consider how I got there, doesn't consider the measurement, doesn't consider the measurement scale, anything like that. What it's going to do, it's going to try and just find that geometric best aspect possible. And so what I'm going to do is I'm going to look at how much did each of the variables contribute to the principal components. All right, so one thing that you'll notice when you do principal component analysis or factor analysis, anything like that, typically, frequently, if I'm dealing with, like, let's say humans, well, I'll see like an overall aspect. So if I'm talking about education or intelligence, usually, not 100%, the first principal component will correspond, roughly speaking, to like overall academic ability, overall intelligence. If I'm doing something with crime, where I have like burglaries, murder, rape, theft, arson, stuff like that, the first principal component will usually correspond to overall crime. Not worrying about what is each type of crime, but what is the overall crime rate for like the region of interest. And if I do this for, let's say, like that decathlon data we were looking at, the first principal component will roughly correspond to a measurement of overall athletic ability. And so now what I want to be able to do, I want to just kind of see how are the individual variables impacting this. So I'm only going to worry about the ones that have like the greater values. So how I usually proceed with this is that in real life, when I'm doing this, I only look at the big ones first, and then I go biggest values in absolute value terms. And then I go a little bit lower, a little bit lower, a little bit lower until I feel like I'm not getting this like random fluctuations aspect. When I was preparing for this, I just played around with it. I felt like greater than 0.15 for this particular project was the appropriate cutoff. And so how I usually do this is, you see how I've got this sorted out? I sort it out. I see meter performance and gain, and then 2 of the gains. Then I've got meter performance, symmetry, signal strength 5, and I've got gains. This is my 0.2 criteria, 0.19. I see that I've got signal strength, crossflow, symmetry, performance, and now I've got a bunch of other gains. Now I notice that as I work through this, and so when I do this professionally, when I did this beforehand, I just keep on looking at positive and negatives and only look at the big ones until I get to a certain point where I don't think it's really of any consequence. And looking at this, I noticed that I've got signal strength is coming up pretty big in this. I notice that gains are in the opposite direction. See, we've got, transit time and signal quality. All right, so here you'll notice I've got all of my negatives. Here I've got all of my positives. And so this grouping is like evaluating gains versus all of the others in like an opposite direction. So if I was looking at something involved in, let's say, like that overall crime rate, then what I would typically see for something like that would be that burglary would have a positive number. And I would see that theft has a positive number, arson has a positive number, murder has a positive number, rape has a positive number. And they would all contribute. It would just be a question of how much do they contribute. For overall athleticism, let's say we're talking about like the throws in the decathlon. Let's say the throws and long jump, high jump, all be positive numbers, but then the speed events typically will have negative numbers because smaller number is better performance. And so I'm looking at this and I see that there's kind of like a contrasting aspect between gains and signal quality are the two big ones that are jumping out at this. And so if I was to do like a factor analysis further down the road, I would probably look to see, study like signal strength, contrasting gains, like down the road for this. The other ones, they're important and they're useful, but for the purpose of like a factor analysis where I'm trying to find like hidden variables, I would definitely want to check signal strength in being contrasted with gains. Like I think there's probably something going on in this data set. And so now here is the bar plot just for us to be able to see what it looks like. And so here you can see, here are some variables that I just chose to keep out of that consideration because they were so small in magnitude that they weren't contributing. Any questions about this? All right, so what is the goal in using principal components? Yeah, reduce dimensions. And so why would we want to reduce dimensions? Reduce overfitting. That is the, from machine learning point of view, that is the big one. That's the one that we really care about. There's other uses like studying correlation between variables that I haven't touched on at all. Finding hidden variables like intelligence. We can't measure intelligence directly. We can observe the outcome from intelligence. Any other questions? If none, then we will go on to string manipulation. All right, for me professionally, I use string manipulation probably 4 out of 5 days at work. So the number one use for me is that when I have data that's categorical, but I don't have a consistent coding of the data, or if I have text analytics that I need to run, that closed up a project a couple weeks ago that was heavy on this. Another one is that for my visualizations, I can only label things so with like such long names. Imagine if I have like, let's say states are included in, I've got city and I've got state is spelled out. In that situation, when I do my visualization, I label things like, having, Pennsylvania and Massachusetts in there, that's going to take up a lot of real estate on my visualizations. And so then that means if I've got the label real long, that either I'm going to overlap or I'm going to squeeze out something else. And so string manipulation gives me a way of changing my labels on it. And so that's one that I've had to do a lot. All right, so string manipulation is the process of changing character strings So, if I've got, text, we're going to call that a string. And something that is important for us is that the same data can be recorded in different manners. So for example, this could be me 3 different ways. Now, as humans, we look at that and we go, yes, that Aaron Smith and Smith, Aaron are the same. But the computer doesn't know that. And so the techniques that we're going to talk about now gives us ways that to like go through and try to convert Aaron Smith to Smith, Aaron, and try to find like patterns so that we can get a common, get things written down in a common manner. This can also become very important in the situation where I have character strings for dates. So a lot of people do dates in a lot of different ways. And so we potentially could use string manipulation. At this point, a lot of packages in R and in Python gives us tools for converting different ways of writing dates into a consistent format. But if we get into like a really weird situation, we might have to do it manually, and these techniques work. Your string manipulation phase will make or break your text analytics models. If you want to do natural language processing, you want to do bag of words, sentiment analysis, your string manipulation will make or break your project. Like 100%, I promise you, you must do this. A lot of people skip over this and they get weaker models for it. So here's an example. Let's say that we had these words going. We had the word jump, all caps. We had jumping, jumped with a capital J, and jumper. Now, these are all words in the English dictionary, right? Now, if I'm doing machine learning, do I want these to be different words, or do I want these to be the same? Probably the same. Now, if I'm talking about a very specific situation, let's say like, I run like a bungee jumping company, or let's say I run corporate for a franchise of trampoline, companies, something like that, where kids go and jump on trampolines. Maybe I would want it to be like separate words, but more than likely, we're going to want all these to be converted down to the word jump. And so when I do my actual modeling, I want all of these converted down to one common version. All right, so here is one order that I ran. So I had data sets. I was working on a project, and this was the order in which I executed my string manipulation. This is just one proposed manner. Something about this is that in string manipulation, order matters in how you choose it. Basically, you want to hit the heavy stuff first, and you want to check to make sure, be mindful of the order that you do things in. So on the particular project I was working on, I felt like removing all the URLs first was a good one, then removing contractions, special characters, and then punctuations. All right, so for this, when I got to this step, remove punctuations for what I was working on, I got rid of all of my hyphens. I got rid of all the underscores. I got rid of all of the slashes. I got rid of all the question marks, exclamations, periods, etc. Now, if I removed punctuations first, then words in websites would have been preserved. So like my website is statistics.ninja. So if I remove punctuation first, that dot would have been removed, and the word statistics and ninja would have been left after that. Now, maybe you think that the words in a URL are important. So like if you're looking at my stuff and the word ninja would be important and informative, then it would be okay to remove the punctuations first, but more than likely you probably want to remove URLs first. Now here I chose to remove numbers. And that was because just off of this data set, the numbers really were not consistent on like magnitude. Like people, this was working with tweets, similar to what we're going to be talking about on the next one. When people start doing tweets and start doing numbers, they just like, they go nuts at times. And it's hard to convert, you know, like people use numbers to like represent words. You know, like if they do like 3V for heart, something like that 3 is no, you know, it's not informative. Now, something we'll want to do is get rid of empty white space. So if somebody has like extra spaces between terms, we want to get rid of that, trim it down. We want to replace symbols. And so, yeah. So if someone's got symbols going on in there, we want to get rid of it or replace it, depending on what it is. Also, if I have international characters, so if I have like cafe, where we put, you know, a tilde on one of the vowels, then the computer will think that's different than just regular cafe without. And so we want to, you know, whatever words we have in there, we want a consistent presentation if we would want the computer to consider them the same. Converting to lowercase. Now removing stop words. If you consider the words for, and, nor, but, or, yet, so. If I told you that those words were in a message that I sent out, do you know what topic I'm talking about? No. So stop words are words that they're useful for the purpose of communicating with humans, but by themselves, they're not informative. If I was to say, let's say, wheel, tire, brakes, pedal, what am I talking about? Some sort of vehicle, right? So off of 4 words, you know the topic. If I was to say for, and, nor, but, or, yet, so, you've got what, 7 words, and you still have no idea what I'm talking about. So stop words are words that are not informative to what we're talking about. Another good example of that, if I was to do an analysis of, let's say, pediatric medical journals, the word pediatric would tell me nothing, right? Because it's, you know, these are all pediatric medical journals. The word pediatric is going to come up over and over and over, so it doesn't distinguish. Now, the word cardiac or emergency or respiratory would be informative. Now, if I'm talking about general, like medical journals, and I see the word pediatric, that is informative because that tells me I'm in a special situation of dealing with children. And so stop words, like our first line of stop words, are going to be the ones that just in general are not informative. After that, we're going to remove words that are not informative for the situation. Now, replacing abbreviations. So this would be something like for states that I want a consistent representation of words. Stemming words, that is taking similar words and putting them into one format, like all the jumps. And then we can complete the words. And now here, okay, so this is, after I'm done going through all of this, what I did was I checked to see, do I have words that are coming up over and over and over? Well, if it's coming up over and over and over for this particular situation, it's probably not going to be informative. And then I convert to a corpus, which is just a format for storing the data. Now, something that can be very, very useful is that this package here, QDAP regx, which it stands for regular expressions, this will go through and this will remove things for us quick and easy. I have not found a better way to do this within R. So like this function removes Twitter tags. And usually when you start running functions like this, you want these to be early in your process.
Do you have like a library, like regular expression strings that will load up for.
Yeah. All right, so the storage format for strings, usually most of the time, strings for the purpose of like NLP, for the purpose of bag of words cinema analysis, most of the time it's either going to be in a vector, it's going to be a column of a data frame, or in a corpus. So like in the project I referenced to earlier this evening, there was a column called short description that had, there were two columns, like document deviated from and short description were the two text fields I had for that particular activity. And so there were two different columns. For this purpose, I had to put them together into one using the paste function, which we'll talk about on the next slide. All right, so there are several packages in R to tackle this. So one of the things about R that makes it really great is it's open source. So a lot of people are working to give you good tools. One major disadvantage is that you can have packages that do similar things, and it's not really clear which one's the best choice. And so the two that I stick with the most is base R, the ones that are just in the regular R package, and string R. String R has, for almost everything I can think of, is the way to go for most of the things. String R is a little bit faster. It's in the tidyverse, and it handles missing values much better. So if I had a column of text data and there was a missing value, base R doesn't handle that well. Stringer handles that much better. Now the TM package has very specific tools for handling the data after it's in a corpus. So a corpus is just a format for storing our text data. The base R and string R version wants things to be in vectors or in data frame fields. What we're going to end up doing most of the time is, like, we'll work on things in vectors and data frames, convert to a corpus, and then from the corpus, we start doing our text analytics. Once it's in a corpus, usually we want to use the TM package options, their functions to handle things. And specifically, we'll use the TM map for that. Overall, string R is better than base R, in my opinion. I learned base R first. And so if you look at my code, I tend to do base R more just because I'm old, I learned it, I don't want to do it the new way. But for things like string, if I want to extract values, so let's say, and I had to use this on that project, I need to extract specific numbers. Let's say I need to extract zip codes, I need to extract street addresses, city names, stuff like that. Stringer has just a better functionality. All right, so now here are the heavy hitters, the ones that I use probably the most in my work. So with these, so here is kind of like a, what I did, I tried to go through, grab the functions that I use a lot, grab the version for base R, the version for string R, and then give you a description of what it does. So like today, I use the paste function. I did that when I was doing my ggplot work, when I was doing my visualizations for work. This is to concatenate strings. So I want to like glue them together. So like if I had a column that was first name, last name, but I want the person's name together. So Aaron is in one column, Smith is in another. I want Aaron Smith. I put it into the paste function and puts them together. So now the number of characters or string length will tell me the number of characters I have in there. So for example, let's say that I have ID numbers and I have different batches of ID numbers. This happened at where I worked before. There were two different lengths of ID numbers. Everybody with a shorter ID number was from like they've been with the organization for a very long time. At some point in the organization's history, they switched to ID numbers that were 6 digits long. And so if I want to know, if I want an idea of how long someone had been with the organization, I could just go off of the number of characters in their ID number. And that gave me at least an idea. Now for the substring function, what this does, this extracts by position. This is an important aspect, is that it goes by position. So how I use this today, let's say that I have, this is date. What I needed today, today's the 13th. Okay. I needed the year and the month. This is something I did today. You'll notice that this is position 1, 2, 3, 4, 5, 6, 7, 8, 9, and then position 10. What I did using the substring function to get the month, I put start equals 1 and stop equals 7. So for each row of data, because it was in a character field, and in fact, it had more things in there because it also had time. And for my purpose, I don't really care what time of day it happened. I just needed the year and I needed the month. And so then I just said start and stop of 1 and 7, gave me year dash month. And you'll notice that immediately it'll have it in the correct order. The dictionary order is equal to the actual chronological order, which was very nice for what I did. So that is by position. Now there's going to be another function for str extract all. What this will do, this function, it will go through, and if I tell it to find a pattern and extract it. So something I could do, I could say find 3 digits hyphen 3 digits hyphen 4 digits. And that would be a way for me to extract phone numbers out of a field. And then now grep-l and string detect, what these do, these look for is a pattern appearing somewhere. So let's say I'm only interested in records that have the last name Smith somewhere in there. Maybe the beginning, maybe the end, maybe the middle. I could use these functions to say, hey, find wherever there is a Smith mentioned. And then, there's, oh yeah, so this one grabs the string detect. It'll grab the value for you. String count, they'll tell you the number of times. So let's say that I have records and I want to know how many times does the name Smith come up in a particular record. Now the split, what this does is it goes through and this will break up your data. So where this becomes very useful is, let's say I have a column of data, in some way use semicolons to indicate a different field of data. This is something that came up for me at work. It was the value semicolon, value semicolon, value semicolon was all in there. And if there was no value, I just had 2 adjacent semicolons. Well, this string split, I said, hey, split it up by semicolons, and it, boom, it worked out, what's what. It got the data worked out for me. And so this becomes important because when somebody hands you data, they're going to hand you the data however it is. They're not going to go through and clean it up for you. This function here of the string split you can use it to go through and split up fields that you like visually it should be split up, but you need a function you need the computer to actually do it for you. Now this function goes through sub and str replace, finds a pattern and replaces it one time. So let's say that I need to do an abbreviation so I've got data that has city and then state, or maybe just state. For my visualizations, I don't want the full name of Florida because it's going to take too much space. I just want the abbreviation. I can say go in and find Florida, replace it with FL using that. Now, these two here, it's not highlighting very well, but is that it will just do it on the first occurrence. G sub and SCR replace all will replace all of them. Every time you see Florida, I get FL instead. Now, the SCR view and view all, these are useful for just like quickly looking at it. It's like the view function in our studio. Now, converting to all upper or all lower, almost always you want a consistent presentation in your work. And so usually every time I've seen somebody else do work, they've always converted everything to lower. And then if I want to convert to title case or sentence, I've used this personally when I am doing visualizations. So like something I didn't do it today, but I could have done it, is that I had categorical data, and the data that as it was presented to me was all lowercase. Now, when I do like a plot, I would like it to be in title case, because what I was doing, I was putting the variable name up in the title area of my ggplot. And you know, when I present it to stakeholders, I want it to look professional. I want a title to be grammatically correct as a title. And so to title case has been useful for me. And this one I have used a few times for international characters. This chart R.
When you're working with like a lot of text data, is it going to be like arrays of single words, or maybe a couple word phrases, or is it going to be like, you know, in some cases one variable that's like a paragraph text?
So it depends. So imagine the situation that you want to analyze, you know, medical journals. So the one that's really big in academics is going to be, of course, with journals.
Yeah.
You might want to do it over an entire journal, like one issue of a journal. So then you would want to have like all the words in the journal into one big long data set. Another one, maybe you are interested in analyzing journal article to journal article. Then each article is one long text piece itself, or you could break it down into paragraphs, into sentences, and depending on how you want, depending on what your project is, will dictate that.
So when you're calling those functions on it, that's hitting over, say, a variable that you had in memory R.
Yes.
And then if you add that up to, like, say, some kind of like array vector collection,
Yeah.
how to phrase it, you can run that call on that array and it just runs. You don't have to loop it, right?
Yeah.
Okay.
Yeah. So let's say that I'm interested in a famous person's tweets. Then like each individual tweet is one item. Let's say I have it in a data frame. Then I drop, so I have it in a data frame. Each row has one tweet in it. And then all the tweets are in the same column. I drop that entire column into one of these functions, and it executes all over them.
Understood. Thank you.
Now, the string I package is another option for string manipulation. From my view, this is not as popular as string R. String R has eclipsed it in functionality, but it's still a good choice. Now, here are some other tools that we can use. So after my function is in a corpus, usually like the base R and stringer are a little bit trickier to use. The ones that are with TM package tend to be better to work with once I'm already in a corpus. Now, this function, this bracket one, what this will do, this will look for words that are in brackets. So like, you know, when someone's sending a message, they put parentheses so that as like a side note. If I don't want the side note, I can get rid of it. Here, this will replace numbers with the word equivalents. So if instead of like 1000000, I want 1 million, it will go through and figure that out for me. Here we can replace abbreviations, and the package actually has a data set which will show what the abbreviations are, what they get converted over to. We can replace contractions if we want. Usually words that are contractions, most of the time will be stop words for us. But depending on what we're doing, could be useful. Replacing symbols with the word equivalents, such as dollar signs. So instead of a dollar sign, we have the word dollars. Here, this will remove URLs. And then you've got a special one for Twitter URLs. And so there are tons and tons of, this package has a pretty big list, but these are the ones I think are the most useful. All right, so now storage format is going to be an issue. So in a lot of times that we're working through our projects, we're going to put something into a corpus. For our purpose, a corpus is just how it's stored. It's just it ends up just being a faster, better format for storing our text as we're working on it, as we're doing our analytics. So once it's in the different formats, vector source, what this one is an important one for my personal work is that I'll take a vector of strings and then convert it to a vector. Data frame source if it's in the data frame format. This is a volatile corpus. So the volatile corpi are intended to be manipulated more. And so that's usually the ones that, you know, if you're going to create it and save it, not touch it, you want just regular corpus. But usually for us, the volatile corpus is the way to go. One thing that is kind of a pain is once it's in the special format, it's hard to take a look at it. So the function inspect is a way to look at what's in here. And then we also have from the NLP package, we can grab the content or the metadata of an R object. Once we get into this realm, it gets a little bit harder to see what is it that I'm actually working with. All right, now for removing stop words, we have several options. And so the TM stop words function is probably the most frequently used that I could find. And you know, we're just going to use this to get rid of things. So one thing that we have to have a list of words we want to remove. And so what we need to do, we need to either by default settings or by a list that we actually want, we need to select words to be removed. So if I remember, I believe English is the default setting, but we can also use kind equals smart. There's another list of stop words to remove. So QDAP dictionaries also has so here's the top most common words used in the English language according to somebody of the top 25, top 100, top 200. For every project I've been on, removing the top 200 as you know would be better than removing the top 25. Usually, most of the time you want to remove a little bit more than less. And we can see the number of words in each of these groups. And then we can use the remove words function to remove specific words that we know we want to get rid of. Like we can using, and we can specify like special lists. So like if I'm, you know, in the situation where I'm talking about, you know, pediatric journals, the word pediatric or medicine is not going to be informative. Now, stem and complete. Stemming is the process of converting all your words to a common format. And then completing is going through and expanding it out. So if I have complicated, complications, complicatedly, which is a word, I can stem these all to complete. All right, so now what's going to happen is every time I see some variation of complication, complicated, etc., it's going to get converted when I stem to complete. Now, for the purpose of data mining, that is a very good format to present, because if I'm doing data mining, like we know I did stemming, I stemmed my words. And so I'm just going to stem my words, I'm going to run through it. But when I go to present my results to stakeholders, do you think they're going to appreciate complete? They're going to look at that and immediately they're going to question, what is that word? That's not the English language. You're an idiot, you messed up. And they start thinking about the moment that you get them off track of what you're trying to say, things can only go sideways. So completing, stem completion is going through and finding every time I see complete, I'm going to pick a common version. I'm going to just pick one of the multiple ones that got converted over. I'm going to pick one, and all of them are going to get replaced with that version. So stemming is very quick, but completion can take a long time. It can take a really long time. So if I don't have to, I don't do it. But if I'm going to show my results to somebody, like if I'm showing it to my boss is okay with this type of, this understanding, just show it, it's good, not going to worry about it. My boss's boss, no, I have to do stem completion. And we can use the TM map function to do this on a corpora after it's already established. All right, so now bag of words. Okay, the idea here in bag of words is that I'm going to, for every single record I have, so like every single journal, there's going to be a row. Every single word in my data set is going to have a column. And I'm either going to put a 1 if that word appears in the document, or I'm going to put the number of times it appears in the document. So we have two different choices. We can either do a binary, where 1 means it appears 1 or more times, 0 means it appears 0, or I could go with the counts. And we have to make a choice on which one we want to use. A document term matrix. Remember, when I talk about matrices, it's always rows before columns, right? Rows before columns, rows before columns. A document term matrix means that each document corresponds to a row, each term corresponds to a column. When I have a term document matrix, each row corresponds to a term, a word, and each column corresponds to a document. And so we just need to keep it straight which one we're going to be using. Most of the time for our purposes, it's going to be a document term matrix, a DTM. Now, after we do this, we're going to want to remove words that only appear a few times. So remember how if I have, the more predictor variables I have, the more prone to overfitting I am. If I have 10,000 documents and a word appears 1 time out of all of those documents, it's just a random fluctuation from our point of view. It's non-informative, it's not helpful. I need to get rid of that. And so words that appear super frequently, I need to remove. Words that appear very rarely are sparse, mostly zeros, I need to get rid of them. In general, our document term matrices are going to have over 90% of zeros. That's going to be typical. So when we remove sparse terms, we're going to say, hey, I only want columns that have, no more than 95% sparse. And that is normal, that's typical for this field. And then of course, we're going to be doing our visualizations. So here are 4 major ones: word clouds, commonality clouds, pyramid plots, and word associates. So word clouds, we've all seen these, right? Has anyone not seen a word cloud? My opinion is that word clouds feel more informative than they really are. They don't actually tell you, but they're kind of like the pie charts. of text analytics, like a pie chart. Like people feel like they're learning something, but it's not really as informative as it feels like. But people will accept it, even though we know we can do better. If my clientele will accept my output, that's my number one goal, is to get them to have buy-in. So I don't like word clouds, but I use them every single time because I know that people will go with it. Commonality clouds, what this does is that this does like a bar plots of like two different groups, let's say, and I can check to see what's the frequency of each word if I'm looking for contrast. And then the associate graph, conceptually, the idea is if words are appearing together in a document frequently, then they're connected to each other. I can make a graph. If I have a lot of words, it's just too big of a graph to be informative. I've never used it professionally, but I could see the potential for it. Any questions? All right, then we will get to our last topic of the night. And we're actually going to be doing text analytics. All right, so I pulled this data when the Democratic primaries were going on. So when for the election where Trump and Biden were, running head to head together, before it was just Biden, there were, a bunch of Democrats trying to get the nomination before it became Biden. And so when I decided to pull the data, this was, a while back ago, and you can actually see when I built this. All these were people who were going for the presidency at the time. We know the outcome, we know what happened, but their tweets are still useful for this purpose. And so for this example I want to run through, I want to take each of these politicians and I want to analyze their tweets from this point of view. All right, so here, if I'm just loading my data. Here's the file path on my computer for it. And you'll notice I'm using lapply to make this faster, quicker, easier. And then I'm just cleaning things up so it's a little bit easier to work with. So I'm just taking their names. So some of the candidates changed their names during the campaign on their Twitter names. And so I just wanted to get the most frequent version that they went with. And so here I'm just changing it was only like one or two changed their names mid-campaign on Twitter. I'm just changing that up. And so what I'm going to do in the end, I want to be able to predict who wrote the tweet. So if you were to run up to me and you said, I have a tweet from a politician, who wrote this? I want to be able to see, I want to create a predictive model to make the prediction. So of course we would never actually do this, but you could see where this would be useful. In so like you can imagine, let's say I was working in insurance, if I could take the text from like the notes of an auditor and then use those notes to try and predict, is this client going to be costly for us in the upcoming year, so that we could, have an auditor go through audit a policy and then off of their notes say yes or no to having them as a client. So, we can get rid of people, insurance can get rid of people so that they stay profitable. And so here I'm just cleaning it to just two columns. I have the target variable, which is the author, and I have the text, which is the actual tweet itself. And so here, how am I going to do this? First thing I chose to do was convert everything to lowercase, then remove Twitter URLs and then regular URLs. When I was working on this, I'm pretty sure this did the job, but just to make sure, I went ahead and ran a second URL just to get it clean. Then I removed hashtags. This is one that I really debated back and forth on doing, because the hashtag itself would be informative, right, to what the person is talking about. But I felt like just playing around with it, working with it, it was slightly better to remove the hashtag. But you know, if you ran this and you said, hey, no, you should keep it because of XYZ, I definitely wouldn't argue with you. And then here I removed tags because we're all dealing, everything's a tweet. I removed emoticons. I removed email addresses. There weren't very many of those in this. And then I started removing things that were between. And so if you actually do the raw extraction of tweets, you'll notice that there's a special use for putting things in the inequality symbols. And I just wanted to, you know, get rid of it, make it clean. And then at this point, I looked through the individual characters and I found these things as special characters functionally within Twitter. And here I'm just converting it over to what it should be. So here I'm just deleting it. Here I am converting this to an apostrophe. And so, you know, looking through the actual data, I noticed that there was an international A, international S, and so on. And so I just went through and I replaced the American English version, just so that I had more consistent formats. And now, before I ran these steps here, well, actually, after every single step, I like took a look at my data. And when I got to this point, I had taken a pretty good hard look at my data, at the tweets to see what is in there, what do I have, what's left. Because at this point, like, would you, if you know, if you had text analytics to do, would you have anticipated that that symbol would be in there? Probably not. I mean, maybe you know something I don't, but I just chose to look. I'm going to look specifically at what I have, see if there's anything I missed, and then you know, either make a special function, find a function, or run a function to adjust for it. And that's what I was doing here. And so here we can see.
Dr. Smith,
Yes.
how do you like know what's in it? Like if you have such a large data set that you don't really get the chance to like scroll through everything, do you think it's just like best to just kind of like do everything?
All right, so one thing that I have done, and this could take a long time. Let's say that V is just my vector of text. See, it's unlist x equals str split. I think this is what I want. Let me double check this. Yeah, it's X and split. Okay, so what this will do, okay, I'm just going to put a bunch of gobbledygook into this. All right, so it's just all junk, but conceptually, I hope this shows. All right, so what this does, let's look at what you notice I have 3 items in this string vector. If I run the string split on this, you'll notice that it's gone through in the same order that appears here. I have each of these individual characters. And so what I did to get a feel for what's going on, and get these sorts. So to try and find like individual things to see what was going on in there, I can use this to figure out like what is actually in there. And I could also use unique. And so here I can see what are the actual values. And so, and you'll notice that punctuations are, and when I hit the sort, the special characters, punctuations are always first, then numbers, and then letters go, see, it's lowercase and uppercase, it's lowercase then uppercase, like that. And so by doing it this way, I can see like what are the weird characters that are coming out. So if I had, let's see, yeah, so here that's a special character that's coming into play. Yeah, so if I have like some of the more recent ASCII characters coming in, they'll appear in this region of it'll be either here after I sort it, or it'll be in this, like at this end. And so that way I can spot it, I can find it, and I can adjust it. Does that help?
Yes, it does. Thank you.
Yeah. Yeah. So the big trick is the substring function to break it up, and putting that right there breaks it up into individual characters. And notice that here I have a double slash, but that still gets treated as just one character because that's a special character itself. And that's how R handles stuff. Good question. Any other questions? All right, so now here I'm just digging into individual things. Like here, this is special character. I can't remember what it is. But you can see that it gets preserved right there. Yeah, and all of this is just particular to this data set. I'm just working through replacing stuff. And something that you'll notice is that when I make my replacements, I always put in like extra white space. I put an extra space in there because I don't want things to be connected. I don't want to, incorrectly put words together. It's easy to remove extra white space, extra spaces later down the road. And so here, this really wasn't necessary on this. I just kind of included these just to be, just to show these off, make sure you guys have these tools for what you need to do. But, there's a function for moving phone numbers and zip codes and time. Really, I don't think any of these were needed for this analysis, but I wanted to make sure that you guys saw it. So that way you would, because I could see you definitely needing this down the road. And so here I'm doing the replacements, just special, weird characters that just happen to be in there, slip through. And so here, this is another way that I can replace all the punctuations. This is a regular expression for punctuation. Here's regular expression for a number. I could also do //D. And now here, this is my quick and dirty technique of getting rid. So if let's say I need a fast analysis, I just want to do like my bazooka, not even considering what's really going on. If I want to get every stuff that's weird out, this is my personal trick, is that this gets rid of all of the weird characters out of my data sets. The lowercase w, the //w, is all the printable characters, and everything else is capital. / lowercase w is everything it's printable. / capital W is everything that's not printable. Now I go through and remove stop words, and I usually like to do this multiple times because there's substantial overlap between these lists of words, but there's a few in here that are not in here. And there's a few in here that are not in here. So usually I find it's best to be aggressive about removing stop words most of the time. Exceptions would be if I'm in like a small amount of words situation, but I've yet to be burned on removing too much. This step here, this is another way, this is a regular expression for one or more spaces. So if it's a star, it's 0 or more. If it's a plus sign, it's 1 or more. So if I have 1 or more spaces, I'm going to replace it with just 1 space. And dollar symbols came up a lot because we're talking about taxes and budget and stuff like that. So politicians love to go on about that. I ended up just not even dealing with it. I removed it from it. And so now working on this project, this is by the time I get to here, after I've worked on all this stuff, I'm stemming my documents. So this, I'm converting similar words to the same roots. At this point, I put some effort into it. I want to save my output. So I go ahead and I write the CSV to remember it so I can look at it later. And so if I return to the project, I'm just going to be using the cleaned version of everything. I'm not, at this point in my project, and as long as everything goes right, I'm never going to touch my original data again. So it can keep going forward. I'm only going to work with my clean data. Here I'm converting it to the format to be able to do my document term matrix, because R wants this particular format. It wants a corpus for me to be able to do document term matrices. And that is a faster, more efficient way to approach it than if I wanted to do it some other way. Here I'm making my document term matrix. Each row corresponds to a tweet. Each column corresponds to a particular word that's been stemmed, a stemmed word, and then the entries are the number of times that word appears in the tweets. Now, removing sparse terms. All right, so this tells me that I'm allowing a lot of sparsity in there. So that means that there's probably a wide variety of words going on. And if I do as.matrix, I can take that count matrix and make it into a classic matrix format in R. So I can see that we've got, over 25,000 tweets and 500 different words to work with. So now let's go ahead and visualize what's going on. We can get term frequency by getting the column sums. Easy peasy way, because I have already computed the data matrix. And so here it's real easy for me to see what are the most frequent words. And so we can see fight, country, amp, American, Trump, and president. All right, remember that we're talking about presidential candidates. Fight. Fight is the #1 word of all their tweets. Does that say something about our politicians? I mean, honestly, it's the most cliche word. Like, so now, since I ran this analysis, every time it's usually for like the local, congressman or whatever, I saw one today, they'll say, I'll fight for X, Y, Z. And like, everybody says they'll fight. Like, it's all the same. Country. Is country informative for this purpose? No. Like, we know which country they're talking about, right? What about American? Is American informative for the purpose of the presidency? What about president? Is president informative? All right, so really, all of those words are stop words. So if I was to rerun this analysis, I would want to remove those and then, start all over again. Now, fight is actually interesting because I think Elizabeth Warren, she was putting fights like up, down, left, and right. And so you can kind of guess where she was in her campaign, because we all know that she dropped out. And so fight was probably, she was trying to like, do CPR on her campaign before she exited. What about AMP? How did AMP get in there? Yeah, it has a special use in Twitter. I've forgotten what it is, but that's their handle. Okay, yeah, it's part of Twitter. So I didn't know this when I was running this. And so I left it in. And so, this is an example of how you go through, you run through a project and you go, oh, well, I should have done X, Y, Z. I would go back up to earlier in my code, fix it, rerun everything. And this is very common of actual real text analytics. Text analytics probably has more than any other aspect of project or any other project I've worked on. Text analytics has more of a go back, fix it, go back, fix it, go back, fix it, just because there's so many ways that, we're just so, everybody writes differently. There's so many nuances. I consider of these words, the only one that is not a stop word is Trump. Because here, exactly what the topic is immediately off of that. So, I find that interesting. So let's go ahead and look at the word cloud. So the word cloud, the bigger it is, the more frequently it was used. And so what do we think were the major topics of the campaign?
Healthcare.
There's healthcare, yep. Yeah, climate. So the Democratic primary is going on, right? So you'll notice that once President Biden got the nomination, like the actual topics changed quite a bit. But during the primary, who are they trying to bolster? Who are they trying to get excited? If I'm in the Democratic primary, who am I trying to get? Am I trying to get every American excited? Democrats only. All right, so you'll notice that there's going to be a lot more like Democrat only topics here than if we were to look at after it was just President Biden and President Trump. And so that it's kind of interesting. Join, is that kind of interesting? Like, why would they put in join?
The thing I think of is when they were trying to get, since there were a lot of candidates going on at the same time, or a lot of campaigns, pretty much one Super Tuesday fits. I think like 7 people dropped out.
Yeah. This was right before a bunch of them dropped. This was like the week before like COVID shut UCF down.
My guess on join would probably be, since we're talking specifically about Twitter here and what they're tweeting,
Yeah.
they're probably asking people people to like join their campaign.
Yes. They're trying to get free labor out of people. To be a successful politician, you have to get people to follow you. To be able, I mean, it's true for any leadership position that ultimately you have to get people to like choose to follow you. Politicians, while they're running, when they're not in office, they have to get people to just like, hey, I'm going to go and I'm going to hand out flyers for you. I'm going to call people and bug them to vote for you. I'm going to donate money. And so that is a huge aspect of a successful political campaign. And so join, I mean, if you look at it, it's like donate or join comes up like every single time. So that's
Support.
yeah, support. Yeah. Yeah.
I was gonna ask, the words are close together vertically, right? Like care plan, I'm assuming is part of the phrase, but like work support, are those two distinct?
Yeah. So position only proximity to center is on this particular algorithm.
Okay.
So if you go to a different word cloud algorithm, it might have where position is important. It's actually randomly distributed.
Okay.
So basically, big and close to center means more frequent. Farther from center means less frequent. And potentially we could have every single word in there, but the position is just a random mishmash. So see, removing sparse terms. So if we were to really dig in, we'll see a bunch of words that just aren't used much. And I'm going to go just skip down to things that are just a little bit more interesting. So here is Amy's. I can't remember how to pronounce her name, but here is her word cloud. You can tell that Iowa was important for her when she was tweeting. She's talking about Trump, and she's got that Twitter thing that I forgot all about, or I didn't know about. Here's Bernie. Worker fight, healthcare is definitely important. Talk about Trump once again. Now here's the one that really surprised me. Trump talks about Trump. that one, I did not expect that. You can tell that he is going after somebody. And talking about the Senate. He's attacking Democrats. But impeach, like a lot of his tweets, that's pretty big, right? One of his major words was impeach. So from the tweets, just going off of this, he's talking about impeach more than anybody else. So, like I don't know if he, I would not be bringing that up. If I've got just me personally. Here's Elizabeth Warren, fight. So I mean, she definitely was trying to portray a certain image. Trump again. President Biden. Talk about Donald Trump quite a bit. And now he talks about himself also. Pete Buttigieg. I mean, he's a mayor. Yeah, so here, something that jumps out about me is that support, plan, okay, I get maybe support and plan could be informative, but president, American, country, today, nation, America, it's like not specific. Like you don't know what topic he's talking about. Then Tom Steyer, he was talking about climate crisis a lot more. Here's Tulsi. She was, I believe she talked about reducing military funding was a big one for her. And she's from Hawaii. I think she's like a major in the National Guard or something like that. All right, so now here I'm just running through, the audience looks tired, so I'm just gonna skip through this, but you can dig through it if you want. Ultimately, I ran through and did a document term matrix of what's up. So here are, when we're looking at associated words, you can see like corruption, constitution, state, office, foreign, American, impeach, unit, run, and Obama. Obama's not in office, but he was a hot topic in these tweets. So here are the words these are all words associated with President Trump. Obama was associated with President Trump. Just kind of interesting.
So those were all from tweets that include both the word president and the word Trump. Because if it could be either, then I guess since Obama was the president, that
I can't remember if it has to be both. It might be the sum of the two columns. Or it might be like correlated, at least correlated with both. I don't know. I have to look at the help documentation. But here is the function to look up, to dig in. Then, okay, so this one is for associated words among Trump. Yeah. So for Obama, if we're looking for the term Obama, we can see that Joe Biden actually used Obama more than anybody. He was the vice president, right? And then President Trump. I find that really interesting. And then there's a huge drop off. Now here is a pyramid plot just to see like the contrast. So here, the one that jumps out the most to me is that impeach. Like impeach is just like Biden's not really talking about it. You would think that would be something he'd be leaning in on. No, President Trump was talking about it far more. But yeah, both of them are talking about Trump. That's. And so, yeah. All right, so I went through and I did a random forest with the tweets. The goal is to predict who was the author off of the counts for each words. And I ended up getting just below 50% accuracy. So something to be mindful of. How many levels did I have of that target variable? Let's see, there were 6, 7, something like that. Something to anticipate when you're doing text analytics or doing categorical target variables. The more levels I have, the more ways I can be wrong. So if I have 2 levels or I have 3, you would expect to see a little bit worse performance on 3 levels than you would on 2, because if I have 2 ways to be wrong on prediction and I have 1 way to be wrong, it's probably going to be easier to spot it. So you'll notice that the accuracy rate in general, as you work through categorical prediction projects, will be worse if you have more levels. Like I had one where I had to predict 13 different levels. And I fought like heck with it to be able to get a decent model. But at a certain point, 13, there are 12 different ways to be wrong. It's hard to miss all 12 when I make a judgment call. Something also to consider when we talk about bag of words, the sentence, the dog bit the boy and the boy bit the dog are the same data for this purpose. And so we don't get that context. We don't get that, that understanding of what's going on. We just go by the raw counts of words. Any questions about this?
That prediction, that was with the exact model that you loaded up prior, where you had some of the, like you said, some of the words that you thought later on were not as important.
Yeah, those were kept in there. Any other questions? Yeah.
And I guess you would say for the number of levels that we have here, 48% is maybe somewhat decent.
Yeah, I mean, I feel like I could improve this. My feel is probably 60% is probably the best I could hope for off of this project. You know, there I might be able to like shave it up, but I think, you know, I don't think it more than 10% improvement would be realistic.
So you would say it's probably useful.
Yeah, because I mean, I did go through and I did clean out a lot of gunk, you know, so it's probably pretty good for the data sets. Yeah, I usually off of your first run, unless there's something you really miss, you're probably not going to get more than a 15% improvement. Any other questions? All right, then I guess we'll go ahead and call it a night. I will stick around if anybody wants to talk. I will stop recording.